Welcome to Lab Life with the Air Force Research Laboratory.
Hi, I'm Michelle.
And I'm Kenneth. Hello, folks. Today we are joined by Dr. Monica Allen to discuss the enlightening world of photonics, plasmonics, and how working for the AFRL family is truly a one-of-a-kind experience.
In 3, 2, 1.
Dr. Allen, welcome to the podcast.
Hi, it's nice to be here.
Yeah, we appreciate you joining us. You're currently a principal research electronics engineer within our munitions directorate, but we'd like to go back in time a little bit to maybe the reason why you're actually talking to us today. There's a moment in American history that kind of changed a lot of our worlds, including yours. You had a calling on September 11th, 2001. It was kind of a pivotal moment for you in your career.
I remember I was a new graduate student. I think we all remember where we were at 9/11, like the exact place is frozen in our minds. But I was a new graduate student at the University of Texas when it happened. It was a day, I think, that shook everybody. And when we heard the news, I remember my advisor calling me and telling me to stay put, not come to the lab, turn on the TV and see what's going on. And don't leave your apartment unless you need to. I really thought it was more like being in Texas, there was a tornado coming down the street or something. But when I actually turned on the TV, it turned out to be much more grim. I had really chosen to move to the US earlier in that year because of the freedom and opportunity it really offers everyone, no matter where you are or where you come from. And seeing that attacked, on that day was very, very disturbing. I decided at that point that I somehow needed to make a difference and do my part. And the best way I could think of was to use my talents as a scientist to help the war fighters that defend this freedom that we had and make our life the way it is possible. And so that's how it changed my perspective, really.
Well, thank you for sharing that very personal moment. It changed your whole life and dedicating your work to defend those freedoms. So from that moment on, you had this passion, this calling. How did you end up connecting with AFRL? I mean, you're a graduate student when this occurred.
And so, as after graduation, my first job opportunity was in industry for a while my husband, Dr. Jeffrey Allen, who also co-leads our team here at Eglin with me, was a graduate student at Duke University. While working there, he started a project with AFRL, and he was very inspired by the people and the quality of the work. He encouraged me to look at different positions and work that was going on in AFRL. And when the time was right, really, when positions opened up, we both decided to apply and really fulfill our collective dream to contribute to this bigger mission. And here we are, research scientists.
I kind of want to focus on the work you're doing now, or kind of the work you started with. So it's a pretty unique area that I think a lot of our viewers or listeners will find very cool. So we have a section we like to call Lab Life 101, where we kind of dive into an idea or concept that people may not be familiar with. And today we're doing photonics. So what is photonics?
So photonics really is the science of light, and which is centered around everything that involves light. So generation, control, detection, and it's both in light waves and photons. Photons, which is, the duality of light, where you see you can be described either as waves or as particles. So photons, which are particles of light. It has many applications. Obviously, we see it all around us, right? Defense, energy, biomedicine, even forensics, yucky things we normally don't think of. But visible light is what most people think of, turning on a switch and illuminating the room. But really, visible light is a very small spectral range of what photonics really encompasses. So our team really conducts research in the whole wide variety of wavelengths that photonics encompasses. And this goes all the way from radio frequency, so microwave, to visible and even infrared light. So imagine night vision goggles.
So to kind of go into that further then for some of our listeners, so you work with a wide spectrum, as you mentioned, a wide spectrum of light and everything else, different waves. So people will have a lot of views of thermal vision that we see, like you said, in movies like Predator or other things, night vision. But when it comes to radio waves, how is that visualized or captured by your team? Like, what does that look like when you're working with radio?
So when we're working with radio waves, to us, we're rather frequency agnostic. So a wave is a wave no matter what frequency, fast or slow. And our goal is to make the best use of what is the best features in those waves. So in radio waves, they're pretty robust. For example, in dispersion in clouds or through dust, things that light can't penetrate through. And so for us, radio waves are useful to circumvent the shortcomings of visible or infrared light.
Okay, very cool. Yeah, I mean that makes perfect sense. And speaking of different cool ways you're utilizing light, the spectrum, and a lot of the work you do, there's a very interesting term that sounds pretty sci-fi. Plasmonics. What is that, and how does that relate to the field of photonics?
And so plasmonics is not a very old field as it's come to maturation. So about the last 10 years, you've seen tremendous growth in the field. And it combines, the reason it's seen that kind of growth is it combines the best of electronics, that is, which is seen in extremely small sizes, your chip scale devices that you see in your computers, etc. And photonics, which is very, very fast speed. Surface plasmons really are electromagnetic waves that propagate along the interface of a conductor and a dielectric. So it's really a sort of, think of an electron that vibrates and hops along the surface between air and back onto the ground for the electron, which is your conductor. It hops along the surface and is confined to that very thin layer between the two interfaces. And so it can carry optical signals and currents through very thin metal circuitry, making photonics and electronics possible on the same chip with very small sizes.
I don't know, Ken. I think I might actually need the remedial course of photonics, not just the 101. But Dr. Allen, that was a great explanation. And you talked to us about the application in your job for the Department of the Air Force. Why do we care about photonics and how things work?
So, there are three major aspects when you think of a munition or a weapon. There's first accuracy. So can we detect and identify the target and then deliver the weapon accurately, even in very harsh speeds and temperatures, because we're traveling really fast, right? There's weight and size. Is it light and small enough to fit in the compact space of an aircraft or a delivery, but still maintain the performance we want? And there's finally cost. After all, weapons are a one-use system. And so we need it to be reasonably priced, yet very high performance. So with that in mind, the team focuses on the following areas of research. So for the first, high-speed detection and imaging. Then we look for multifunction materials for photonics. Really, how can you design and engineer materials to do many different things on the munition so you're not carrying dead weight? Then quantum technologies for timing and sensing to improve our accuracy. And photonics for testing. Everything in our munitions or any other platforms that we have various electronics and chips on them. And photonics provides not only a path to test these and make sure they're not tampered with, but also to enable this built-in hardware assurance so we know whatever we're putting in our systems is safe. At the same time, ordnance, which is the mechanisms that make things blow up, essentially. Ordnance and munition can be optimized by characterization techniques. So we need to make sure we have the best ordnance that we can have. And things like imaging and spectroscopy that are based on photonics can be used to check the efficacies of the blast that we create and also provide a safe path to monitoring the health of our weapons as they're stored and transported. It's kind of an encompassing technology that has broad application.
Yeah, and it's kind of cool to think, especially kind of bringing this to a head, almost like this Moore's Law idea of like being able to have such powerful processing power in such a small package. So it's cool that your family or your team, I should say, has this means to bring down, get these, the circuitry, these systems to actually work in smaller and smaller packages. So as you project and go forward, we'd be interested to hear what your team's day-to-day kind of looks like then, working with such cool high-end tech. Is there really a normal day-to-day, or is it kind of like whatever comes your way, that's what we're going to start doing?
It's a little bit of both. Everybody has exciting days, but we really divide our time between the office and the lab. Once a week, we all come meet up. The team meets up. We look at new ideas and research directions or just simply solutions for ongoing projects. During this time, we get together, we present new papers that we have found over the week, maybe problems that we've encountered during our research endeavors. Then we all brainstorm and really do our best to help each other out so we can make quick progress. And these meetings are also very exciting because sometimes somebody will come up with this, hi, look what I found moment. You find these new forward-looking research areas to not only examine the state of art, but how can we really incorporate it into our work. So the typical day is kind of designing and simulating new designs that we've come up with, which is structures, media, devices, or all of the above. And then once this phase is complete, we are in the lab fabricating and trying them out and characterizing a design. So we want to see if the performance we expected out of our simulations is something that we actually got when we demoed it in the lab. And then if not, then how can we improve this? It's a feedback loop. The ideas that are brought up is always exciting, they're interesting, and everybody, going back and trying something new is something that the team always looks forward to. We have a wide variety of multidisciplinary members in our team, and this mixed perspective also always has been helpful to come up with out-of-the-box solutions that have wide impact. So it's been very exciting.
So touching on perspectives, it's interesting to hear about how your team approaches a lot of these different problem areas or areas that they want to help. Like, hey, we found a new source or new something we want to work on or new cool objective. Can you kind of take our listeners into the lab then and describe what tools are you using? Are these simulation software, actual things that are emitting these light spectrums that you're looking into, or what does it look like when you're doing some of this experimentation?
We have two different labs. We have some that are characterization labs. We certainly have our simulation tools. So we have a variety of tools. We have off-the-shelf simulation tools that we use. Those are mainly the second step. For our more specialized designs, we write our in-house analytical sort of software, and that really helps us understand what is the underlying physics, what's really creating the phenomena that we see. And the simulations are used to verify and really hone in on the right design and optimize performance. Once we make the designs, we try them. We have various characterization equipments that span the spectrum that we're looking at, help us look at performance in every area.
How cool is that? So that's a really neat way of kind of, showing our listeners in a way, like kind of what it looks like to be there on the team. And we have to imagine with a lot of the extensive work you do, the cool stuff you're actually working with in a very hands-on way, but are there any strategic partnerships you have to actually aid along this mission?
While the technical part of the mission is obvious and obviously critical, the part of engaging partners is to leverage their expertise so we can get to our goals faster and more efficiently, but also keep an eye on the strategic perspectives of these collaborations, because that is also a big part of our mission sitting here at AFRL. So we have, over the years, had many international academic partnerships as well as defense agencies.
Are there any other special projects or research efforts your team is working on that you think our listeners should know about?
So, there are two specific areas of research that come to mind. And one is plasmonics. We discussed that a little bit earlier. So our team's pioneering efforts really came up with alternate materials to push plasmonics in the infrared. So before those alternate materials were looked at by the team and characterized, plasmonics was really relegated to the UV and the visible, which are not two regimes of extreme interest to the DoD. Infrared is much more important. So we were able to come up with a material and devices that now really form the baseline for several plasmonic sensors and applications in the infrared. And they provide this highly resonant gain and spectral selectivity that are very important in imaging. And the second one is microwave photonics. And this is not your typical microwave photonics where you're taking light, converting it into an RF signal, and then pushing it down a wire. It's truly an innovative approach to combine RF and optical technology to enable a new class of RF photonic devices that integrates what's the best in RF, which is, it's cheap to fabricate and measure, and extremely ultra-fast speeds of optics, which is light, speed of light, if you will. And so to be able to combine those two unique capabilities is really what this phenomenology enables. And these, I think, will find broad applications in sensing, signal control processing, metrology, etc. But what really is interesting and has really led to the success of these examples I've given you is this tip-to-tip execution of research that the team conducts. So I just want to highlight that.
I was going to say, listening to everything, it really feels like your team is involved so much, like the basic research, the application, the strategic partnerships. What's it feel like? You use the phrase tip to tip. What's it feel like to own all of that part of the R&D process?
And so, for us, tip to tip really means looking at the future needs of the warfighter to come up with solutions. These are often known as pulls, while keeping an eye on interesting phenomena and emerging science to bring functionality we haven't thought of yet for the future battle space. And those are known as pushes. So, the team looks at both push and pull, and that sort of comes from into play with basic research and then the applied research end. We really look at how science can be transformed into a viable design. Once we come up with a concept or design, we look into how the underlying physics can be modeled so we understand what's giving rise to the phenomena. Once we understand this, we come up with the material requirements for the design and simulate these parameters to predict performance. And these material and structure parameters are then used to, once optimized, are used to fabricate the devices. And the deviations are fed back into the simulations to see if the performance is acceptable. And if not, we optimize the design. And this tip to tip methodology, or a feedback loop, if you will, allows the team to have ownership, satisfaction, and we really can see the project through to completion. It also gives us unique insight into every step of the process. So we're not handing off something and wondering what happened to it. And this provides valuable scientific lessons and also builds in-house expertise.
And I think the push and pull that you highlighted, that's something that we hear a lot about from our researchers, because it's not only are we responding immediately to the warfighter saying we need this, but also we're predicting things that they may not have even imagined that they need. And so it's very interesting. And I know another big project that you've worked on is to help bring a national photonics conference to your area to, create those collaborations.
The team is able to be the founders of what is known as the IEEE Rapid, or Research and Applications of Photonics in Defense Conference. It's an annual international conference held in the local Eglin area, which brings together government, academia, and industry in a global forum to present not only fundamental basic research, but also innovative technologies and networking opportunities to build collaborations to solve critical security and defense problems. This is a broad conference. Photonics is a broad area, and so we have to cover many aspects. We look at everything from device physics, algorithms, test and evaluations, just to name a few tracks. And with the broad topics covered, the conference also attracts diverse participation and collaboration from academia, industry, defense, and government agencies to, share technical depth and breadth while networking with peers. And again, this is not relegated, it's not a domestic conference, so you really get to expand your global horizons. It is also a way for looking at how can we perform multidisciplinary work. And we touched on this a little bit earlier, leverage other efforts and look at how research is progressing in other parts of the world as well. This is an opportunity also for our STEM development. There is a Women in Photonics session for diversity, and also workforce development through networking. It's allowed the local workforce to participate in technical sessions that not only via volunteering and technical presentations, but also in leadership opportunities. We think that this has been a tremendous opportunity for all of us SNEs here in this area, and we're very happy to have founded and sustained this conference now leading into its 5th year.
This whole podcast episode, I'll throw a pun in there for Ken. We've barely illuminated a little bit of the work that you do on photonics. I was considering shine a light on, but it's like illuminate. That's a little more powerful.
I love them both.
Thanks, Ken. Your approval means a lot to me. And anyway, so you mentioned it within this conference, doing a lot of things, including STEM, and I know developing the workforce is something very important to you. Your team contributed to a book called Women in Aerospace Materials, writing a chapter. And I'd love for you to just give us a few nuggets out of, the advice and the stories you put in there for our future workforce.
And so, for me, the basic nugget, I think, is aim for the sky. I mean, here's the pun again. We are working for the United States Air Force. We need to fly high, right? And so it's closer than you think. And AFRL, I think, out of all the places I've worked, has very encouraging and motivating people. People are willing to help you along the way. It's important to take their advice and take it in the right sense. And so most successful people in AFRL and outside are happy to mentor and help people along the way. And my advisor actually would always review my work and offer her comments. You would send her a research paper that was in white and black, and then it would come back all red. But it was important because it helped me grow as a researcher and a person. And it really changes your perspective when somebody takes the time to critique your work and understand the difference between harsh criticism versus constructive criticism, and to be able to take that to improve yourself. So it's really all about perspective. You can choose to see the positive, and it'll go a really long way, not only in your attitude, your progress, but also your team.
And that just made me think all the red markups. As a coddled millennial, I think at one point my teacher switched to like the green and the purple pens to be less harsh about, how my English paper could be a little bit better. But memory unlocked there. But, tying our conversation together, ultimately, what does working at AFRL mean to you?
One of you had a slip and said, your family. And, that's really what AFRL is. AFRL is my second family, and my team really is that. They have supported me to achieve my dreams and pursue some very extraordinary research that, I couldn't have even dreamed of maybe a few years ago. And so all this while balancing the demands of a family life. As a woman, that's important. I achieved my dream not only to be a scientist, but I'm very proud to work on the nation's most critical security and defense problems here at AFRL, but also to be a wife and a mother. And what is really amazing, I didn't have to choose between one or the other. My Air Force career really allowed me to do both. It's very exciting and rewarding. At career fair, my son was asked, what does he want to do? And he said, I want to be a scientist just like my mom. And that was amazing.
That is so heartwarming. It really is. Slip up. I mean, I'm glad it all came together. That really we are the AFRL family, and to hear what it's like to be part of it is inspiring. So we want to thank you, Dr. Allen, for taking the time to speak with us today, cover your amazing career, cool stuff about photonics and plasmonics, and how to aim high, like you said. So thank you again for joining us.
Thank you so much.
Make sure to follow us on social media at Facebook, Twitter, LinkedIn, Instagram, and YouTube at AF Research Lab. And remember, stay curious.
Logging off.